Hello friends. Today we are going to look at a new module in convective heat transfer. All these days we were actually looking at convective heat transfer in forced convection and natural convection, both laminar and turbulent. But all of these basically were single phase fluids, that is fluids either in only liquid phase or only gaseous phase. The aggregation because it's basically determined by the properties and reflected by non-dimensional number, Prandtl number. One thing that we need to also have in mind in the sense of a feel for numbers is that when we have only single phase gas flow, okay, so since the gases have a low conductivity, the heat transfer coefficient values that you get out of gas phase would also be lower. So typically the H values in single phase gas flow would be in the order of 0 to 10 for natural convection and 10 to 100 at most for forced convection. This is the typical range of values that you get for single phase gas flow. Laminar, it would be in the lower end, and so this may not be 0, it's actually, you can say 1, okay, because Nusselt number is basically defined as the ratio between the heat transfer in the presence of convection and to that in the absence of convection, which is pure conduction, so it will be 1. So 1 to 10 in natural convection and 10 to 100 in forced convection for gases. This is typical. The higher the turbulence, the higher would be the value. So this could basically maybe go up to 20 at most. So that is the range that you would have. Whereas if you look at single phase liquid flow, since the conductivity of liquids is usually higher, we're not talking about liquid metals, but just look at liquids like water, etc. So let's say water flow, the H value, so you can call it water or properties of the liquid similar to that of water. Then you would have this in the range of 10 to 100 for natural convection and 100 to 1000 or maybe a few thousands, maybe 2000 to 3000 in the case of forced convection with liquids. This is the typical value that you normally expect to get. But when you use systems with phase change, then this heat transfer coefficient goes at least a more order of magnitude or more higher. So we look at convection with phase change. So now phase change we can look at in terms of it could be phase change from gas to liquid or liquid to gas. Solid liquid, liquid solid, basically solid there is no convection at all, it's only liquid. So we are not looking at melting, at least in this chapter. We will be looking at phase change between liquid and vapor. So gas to liquid is nothing but condensation, and liquid to gas is nothing but boiling. We'll look at these two phenomena in the current course in the chapter on convection with phase change. Condensation typically happens in two different kinds of phenomena. That depends on what happens to the liquid that condenses on a solid surface. So suppose I have a cold surface of a solid exposed to a vapor, and the vapor condenses on the solid surface to form a liquid droplet. There can be two possibilities. One possibility is that the liquid droplet wets the surface, that is, its surface tension with the surface is low, and therefore it spreads and has an acute angle of wetting. So suppose I have a vertical plate on which a droplet condenses, the droplet would just spread itself. So if I look at the angle of contact, it will be an acute angle. Okay. So when that happens, then every droplet that condenses on the surface of the solid, it will wet the solid surface and form a film on it. Okay. So suppose there is one droplet that condensed here, there is another droplet that condensed here, there is another droplet. So basically all droplets don't have their own identity, but they just merge with each other by spreading on the solid surface. So you then start getting a film. Okay. So if I start afresh with the drawing, let me just remove this. Okay. So suppose I have a vertical wall like this, okay, which is kept at a temperature T wall, which is less than the saturation temperature of the vapor, which is in this region on this side. Okay, on one side, that is on the right side of the plate, there is, let's say, a vapor, which is, let us for simplicity's sake say that it is kept at a saturation temperature. Okay, so then what happens if T wall is less than T saturation? Then all along the wall, entire wall, the liquids, the vapor starts condensing to form liquid, and the liquid can actually form a film because it is wetting, and because the liquid faces a higher force of gravity due to its higher density, it starts flowing down. So you can see a film that starts flowing down from here, okay, up to a certain distance from the leading edge. Let us say this is X, up to a certain value of X, this film will remain laminar. Okay. So there is this influence of gravity in the downward direction because of which there is flow. After a certain distance, this starts becoming unstable and you get a wavy pattern. And these waves are usually uniform in spacing and in the form of a neat periodic wave. So some instability has crept in and it's becoming wavy instead of having a smooth surface like it had here in the laminar region. Now, after some distance, this wavy also becomes more chaotic. So you get a pattern where the spacing between the waves does not remain uniform, but it starts varying. So if I look at any point in space also the spacing between different waves has different values at different locations. And if I look at one location with time, the rate at which the waves pass through that is also not as uniform as it is in the wavy region. So here it is wavy, here it is turbulent. Okay. So you have this whole thing where there is a formation of a film on top of the solid surface and the condensation is happening. So this is called a film-wise condensation. Okay. In film-wise condensation, what we understand is that there is an additional liquid film that comes between the vapor region, which is at Tsat, and the solid wall, which is at T wall, and therefore there is an additional resistance, and therefore the heat transfer coefficient cannot be as high as a fresh wall, a wall which is completely exposed to the vapor. So in film-wise condensation, you get heat transfer coefficients substantially higher than what we saw in the single phase. So you have these vapor and liquid heat transfer coefficients. If it is vapor alone, it cannot exceed 100 typically, and if it is liquid alone, it typically does not exceed a couple of thousands, maybe at most a couple of thousands. But in film-wise condensation, the values of H can go in the order of 1000 to 10,000 watts per meter square Kelvin. Okay, so this is the value of so all of these are in watts per meter square Kelvin that I wrote the values. Sorry about the missing the units there. So the film-wise condensation shows heat transfer coefficients in the range of 1000 to 10,000 watts per meter square Kelvin, depending on which region you are in. When it is turbulent, the values are higher. When it is laminar, the values are lower. and this is typically what you get in film-wise condensation of typical liquids like water. Okay. The other kind of condensation, so in condensation you can have film-wise condensation, and the other condensation that we can have is what we call the dropwise condensation. So what is dropwise condensation? In dropwise condensation, the surface tension between the liquid droplets that are formed and the surface is quite high. So on the vertical surface, if I have a droplet formed, the droplet stays like this, right, with the angle which is obtuse. Okay, so if I look at the angle, the angle of the liquid from the solid surface is an obtuse angle. Okay, it is not an angle in the case of film-wise condensation. It was an acute angle. Here, the angle is obtuse. So if you look at the angle from here, the angle from here actually is obtuse. So you have this angle, which becomes this. So there is an obtuse angle. Okay, so this angle is what you're looking at. Okay, so the angle is obtuse. So then what happens? The droplet is not able to hold on or wet the surface, but it just flows away, just runs away, exposing the surface once over again, and again a fresh droplet comes. So this happens on what is called the hydrophobic surfaces. You need to understand this word phobic. Phobic is phobia, basically means fear. So this surface is afraid of liquids, right? Hydrophobic is afraid of water. So a surface where it does not hold the water but just gives it away is hydrophobic. So it actually, the water does not stick to it. So you might have seen some kind of leaves, like for example, leaves of lotus or leaves of any, like some of these plants. If you put water on top of it, the water doesn't wet the surface, but it just remains as a droplet and keeps running around on top of it. Right? Similarly, if I have like a metal surface which is smoothly oiled on top, so there is an oil film on a metal surface, you put water on top of it, the water doesn't wet the surface, but it just stays as a blob and then keeps running around. So these surfaces are hydrophobic, and the surface can become hydrophobic either because of its natural surface tension with the liquid that is in contact with it, or because of the textures or micro textures that you can have on the surface. Say for example, if I have a surface on which there are micro patterns which are drawn like this, and each of this, if you look at it in cross section, it might have a small height like this, and if I put a droplet on top of it, the droplet cannot stick because there are gaps in between, and it just becomes hydrophobic. So the surface can be made hydrophobic by multiple different methods, by coating it with oil, by making a texture on it, whatever, and or choosing a combination of surface and liquid so that it does not have its wetting angle is obtuse, right? So if I have this kind of a situation, then whatever condensation happens, the liquid doesn't stick and wet the surface, but just runs away, exposing fresh metal surface once again to allow liquids to come and the vapor to come and condense again. So the additional resistance that we talked about in the film formation here, that resistance is absent, and therefore in dropwise condensation, the heat transfer coefficients are substantially higher. So if I look at the face of the surface like this, the face of the surface would have droplets that are there discretely at different locations, and then you find that these droplets keep running away and fresh droplets get formed. So this is what is called the dropwise condensation, and in dropwise condensation the H values are in the order of 1 lakh, that is 10 to the power of 5 watts per meter square Kelvin. Okay, so this is in that order, so which is very, very high as compared to the heat transfer coefficients that you get using single phase, or even heat transfer coefficient that you get in film-wise condensation. Okay, so for this reason, many heat exchangers try to use the dropwise condensation, particularly where the heat flux requirements are extremely high. you try to use the dropwise condensation by specifically texturing the surfaces, specifically making the surfaces hydrophobic, or just specifically choosing a surface liquid combination such that it is hydrophobic, right? So this is about film-wise and dropwise condensation. We'll talk about boiling in a subsequent chapter. Right now, the film-wise condensation, as you can see, is the closest to the boundary layer theories that we have been looking at: flat plate, external flow condensation, external flow convection. The condensation on a flat plate, vertical flat plate, is very similar. The diagram that I have drawn here, this one, is very similar to natural convection over a vertical flat plate, and therefore we'll start with the analysis of that. Okay. Now let us look at laminar film condensation. On a vertical plate. Okay, so this is one of the simplest configurations that we can analyze, and we can understand the phenomenon of condensation using this. Normally, whenever we have a condensing surface, say for example in a condenser where you're using surfaces on which vapor can be condensed, the vapor is not actually at the saturation temperature, but is at a temperature higher than the saturation temperature. Okay, so if I go back to that diagram that I drew, where this temperature is Tsat, suppose this T vapor is greater than Tsat, then there is an additional phenomenon that happens. What happens? Because as you go to the left, closer to the plate, the temperature of the vapor decreases because the vapor is losing heat to the plate. The vapor on the left side is cooler and the vapor on the right side is warmer, and therefore it sets up a natural convection loop. The cooler vapor, because it is denser, it goes down, and the warmer vapor, which is on the side, goes up, and there is a natural circulation that is typically set up. And if that happens, then there is a flow of vapor vertically downwards adjacent to the liquid film. So what happens because of that is that the liquid film will have an additional drag because of its shear with the vapor flow that is there. Okay. So when the vapor is superheated, then because of natural convection that sets in on the surface, you would have an additional velocity that is imposed on the liquid film by the vapor flow that is adjacent to it. Okay, so that makes the system a little bit more complex in the real cases. In order to analyze it first, we will start with the vapor temperature being equal to saturation temperature, so that we can assume that the vapor remains at saturation and the liquid vapor interface also remains at saturation. Therefore, there is no natural convection that is happening. Only the liquid film is flowing down because the the solid surface is at a temperature lower than the saturation temperature. So all the temperature gradient is confined to the liquid region, and there is no temperature gradient in the vapor, and therefore there is no flow. That is the simplest case. So we will take a case where no vapor flow, or therefore no shear on liquid film from the vapor. Okay, so this is one simplifying assumption that we will take when we go for doing this. So if I write the equation for natural convection in the vertical film that is there, then we can use, with the boundary layer approximation, of course, we'll write the, so this is the plane and this is the laminar film that is formed here. Okay, this is the plate and this is the liquid vapor interface. Here is vapor. okay, which is at temperature Tsat. Okay, this liquid surface will also be at Tsat, whereas this solid surface is at Twall less than Tsat, because of which this liquid film condensation is happening. So if I write the equation for the liquid in this boundary layer, in this thin film, the film is going to be very, very slender, because as soon as the liquid is accumulating, it starts flowing down and forms a thin film of liquid on the surface. Okay, so with boundary layer approximation, I can write this as rho L, which is the density of the liquid, multiplied by U del U by del X plus V del U by del Y, which is the inertia term or the advection term, is equal to minus del P by del X. Now here the X direction is this, and of course the Y direction is this. Okay, so the U is the velocity in the X direction and V is the velocity in the Y direction. This is what we are writing. Okay, del P by del X plus mu L, this is the liquid coefficient of viscosity, and because of boundary layer approximation we can neglect the axial gradient del U by del X or del square U by del X square, so you will only have del squared U by del Y square. Okay, plus there is a gravity term which will be rho liquid into G. Okay, so this is the equation. Now in this, with the boundary layer approximation, I can say that the del P by del X we can say that the del P by del Y inside the liquid film is negligible, and therefore del P by del X will actually be equal to dP by dx. Okay, and what is dP by dx in the surroundings? Because there is a stationary column of vapor that is standing there, so you'll have pressure in the vapor region would be P is equal to P reference or reference pressure minus rho vapor Gz, right? So Gx rather. Okay. So sorry, it is going to be plus rho vapor Gx because x is in the downward direction and G is also in the downward direction. So G is positive. So rho vapor Gx will be the thing with respect to some reference pressure where x is equal to 0. So this, if this is P ref. Okay. As you go down, because of the mass of vapor that is standing on top of it, the pressure will be P reference plus rho v Gx. So if I differentiate to get dP by dx, then the P ref would go off, it will become rho v into G. Okay, so the minus del P by del X will therefore be minus rho v into G. So if I combine these two terms, I'll get rho L minus rho v into G. Okay, so this is the expression that I'll get for the gravity term and the pressure term put together. So if I neglect the inertia term, saying that the film is quite slender and the acceleration of a film can be neglected, then basically the left hand side will go to 0 and we'll just be able to equate these two terms. So you will get mu L into del squared U by del Y square, okay, is equal to, or is equal to minus rho L minus rho V into G, or I can take the mu L down to the other side. So this will go here by mu L. Okay, and you can see that all of these terms are constant with respect to y, and therefore I can directly integrate this to get del u by del y is equal to minus rho L minus rho V into G by mu L into y plus C1. Now we know that at y is equal to delta, u is equal to 0 because sorry, del u by del y equal to 0. That's the edge of the boundary layer, and we also know that u is equal to 0 at y equal to 0. Okay, so using this, using the second condition, that is del u by del y equal to 0 at y is equal to delta. So this is equal to 0 at y equal to delta, tells me that C1 is equal to rho L minus rho V by mu L into G delta. Okay, so if I substitute that into this expression, I'll get this del u by del y is equal to rho L minus rho V into G by mu L multiplied by delta minus y. Okay, so if I integrate it second time to get u, that is going to be equal to rho L minus rho V into G by mu L multiplied by delta y minus y squared by 2 plus C2. Now substitute that this is equal to 0 at y equal to 0. So at y equal to 0, this whole term disappears. Therefore, C2 becomes equal to 0. Okay, so then what I get is u should be equal to, so this is 0. I'll get, if I take out a delta square, then I'll get rho L minus rho V into G delta squared by mu L multiplied by y by delta minus y squared by 2 delta squared. Okay, so this is your expression for velocity profile in the film, where delta is a function of x, which we still need to determine from the remainder of our analysis. Okay. Now, if I write the expression for the local mass flow rate, at x, so we are basically looking at this diagram. So at any x, what will be the mass flow rate? It will basically be the integral of rho u dy from y is equal to 0 to delta. Okay, so integral of rho liquid, which is uniform in the entire region, into u dy, where u is just obtained from the expression that we have got. So we just have to integrate it, and then you get the expression for mass flow rate. Okay, so this will be equal to m dot of any x. This is actually m dot prime, because this is the mass flow rate per unit width of the plate, because if the plate is taken to be unit width perpendicular to the plane of the board that I have drawn here, then it is unit width, and therefore you write a m dot prime. This would actually be equal to integral from y is equal to 0 to delta. Okay, all right. Integral from 0 to delta of rho L into u of y dy into 1, right? Because dy is the thickness, and dy is the this component. This is dy, okay, and the area will be dy multiplied by 1 because the depth-wise the distance is 1 meter. So this is velocity into density into area, which is the mass flow rate per unit width, because this is 1. So now this u of y we already know from here, so we can integrate this. So this becomes equal to rho L can be taken out into delta, because this is y by delta that we need to do. So rho L into delta multiplied by integral from 0 to 1, because now you're going to be integrating with respect to d of y by delta. Then u of y basically is this one. Okay, let me write it in the next line because we need enough space to do that. Let me just do that here. That is equal to rho L into delta okay, so this rho L into delta, and then here the constant terms that I'll again take it out, rho L minus rho V into G delta square by mu L is again a term which is going to come out from this u, and the remainder of u will stay inside. It will become integral from 0 to 1. So you are actually differentiating y by delta, so because there is delta that has come out here. It will be y by delta minus half of y by delta the whole square, that is this term, multiplied by d of y by delta. Okay, so this is basically integral of eta minus eta square by 2 d eta from eta is equal to 0 to 1. So if I integrate this, what happens? This becomes eta squared by 2, and this becomes eta cubed by 6. Right? So it will be half minus 1 by 6, which is actually this is 3 by 6, this is 1 by 6, 2 by 6, this is 1 by 3. Right? So this value actually becomes 1 by 3. So I can just put that as the value 1 by 3 here. So this whole integral is equal to 1 by 3. So then we can write m dot prime of x is equal to rho L into rho L minus rho V into delta cube into G divided by mu L, and there is a 3 that comes here. Is that correct? So you have this rho L into rho L minus rho V into delta cube into G divided by 3 mu L. So this is one expression that we get from here. Okay, so this is m dot at any x. Okay, so this is equal, this is in kg per second per meter. Okay, because this is kg per second per unit width, so this is kg per second meter. So this is the mass flow rate per unit width of the plate that I get at any x value, where this delta is a function of x. So this delta is yet to be evaluated. So once I evaluate the delta, then I'll be able to get all of these things correctly. Okay, so that is the next thing. Similarly, the enthalpy flow rate. This mass flow that goes through this film carries a certain amount of enthalpy. So there is a certain m dot at every section, and there is a certain h dot, if I call it capital H, which is the total enthalpy. That is the enthalpy of the integrated over the whole region. It's not specific enthalpy per unit mass, but it's integrated through the whole stream. Then you also get enthalpy flow rate h dot prime at any x. Again, prime reminds us that it is per unit width of the plate. Okay, so how do you get that? So you can actually write for every dy, you can write the mass flow rate and its specific enthalpy and integrate it over the whole length. And what is the specific enthalpy of the liquid at any location? It's a function of the temperature. So let's write that. this is going to be equal to integral from 0 to delta of rho L into U into mass flow rate. So you will get a dy into 1. So this is the mass flow rate into the specific enthalpy H at any y. Okay. Now what is this H at any y? This H at any y is going to be equal to, so if temperature is T of y, okay, and this at T sat, that is at T equal to T sat, H is going to be equal to HF, sorry. At T is equal to T sat, H is going to be equal to HF, which is the saturated liquid enthalpy of the liquid. And if temperature is less, so T wall is less than T sat, so in the liquid film you will have temperatures between T sat and T wall, which is lower. So at any T, okay, the H will be equal to HF minus Cp liquid times T sat minus T. Correct? So if T sat minus T is 0, then it will be equal to HF, and if T sat minus T is greater than 0, the H will be less than HF. So this is your thing. So H at any y will be equal to this T at any y. So this is the expression that you would have. So I can substitute for that in this expression. So H of y will actually be equal to HF minus Cp liquid times T sat minus T of y. Okay. So if I substitute that, then I get this expression as equal to, okay, let me remove this part. I want to written that below. Okay. So now this is going to be equal to integral from 0 to delta of rho L U of y into HF minus Cp liquid into T sat minus T of y dy. Is that correct? Now let's take this and simplify it further and integrate it. Now I have an expression for u of y already available to me. Okay, and I need to make an assumption for t of y just as I do in integral method. So Nusselt, who did the first analysis of this one, made a very simple assumption saying that in the liquid film the temperature profile is linear. So T at any y is actually okay, T sat minus T at any y divided by T sat minus T wall is equal to 1 minus y by delta. This is the profile, linear profile, straight line profile that Nusselt assumed and used that to evaluate this integral. So that's a simplified form of the integral. The values that you get may be approximate, but still the expression becomes easier to evaluate. So this is the Nusselt assumption, and using that, if I can do this integration, then I get H prime dot at any x, which is the enthalpy flow rate per unit width, is equal to rho L, this dy by, I make it as dy by delta, so I'll put a delta here, and u of y, okay, u of y again I know from here, okay, so this is going to be this quantity inside the integral and these quantities outside the integral, so there will be a rho L minus rho v by mu L into g delta square. So this delta will become delta cube into rho L minus rho v into g divided by mu L, and then I'll have the integral from 0 to 1 of, if I write y by delta is equal to eta, then I'll have a eta minus eta squared by 2 into the temperature profile I'll have to now write Tsat minus Twall would come out here again. Tsat minus Twall. Then I'll have a 1 minus eta d eta. Is that correct? So this has to be integrated. So if I multiply this, I'll get eta minus eta squared by 2 minus eta plus eta cubed by 2. If I integrate this from 0 to 1, right? 1, you multiply this by 1, you get eta minus eta squared by 2, and if I multiply it by minus eta, you get minus eta plus eta cubed by 2. So if I just integrate this, I'll get this becomes eta squared by 2, so half minus 0, and this will become eta cubed by 2, eta cubed by 3, and so it's 1 by minus 1 by 6 minus, again this will be, so this eta and eta actually get cancelled here itself. Sorry, this should be eta square, right? This is eta square, sorry. So I can actually write it more simply. So these two together is minus 3 by 2 eta square. Okay, so here then minus 3 by 2 into eta cubed by 3, so it will become 1 by 3, right? Plus this will become 1 by 2 into eta to the power 4 by 4, so it will be 1 by 8. Okay, so this 3 gets cancelled, and this is half minus half becomes 0, so it becomes actually 1 by 8. Is that correct? So you get a 1 by 8. So if I then substitute it here, since I would like to write it in terms of m dot prime, and m dot prime itself is rho l into rho l minus rho v into delta cube by g by 3 mu l. So I'll put a 3 here, inside here, and take out a 3 separately on the other side. So this will become equal to m dot prime at x multiplied by, that will be a 3 by 8 into, okay, so okay, what did I make a mistake about there? All right, this is a HF minus thing I missed out. Okay, so this is not simply this term, but there is a difference. Okay, so let's erase all of this and come again. Okay, so this integral is anyway required, so let us keep that. Let's write it from here. H dot prime of x is equal to integral, okay, rho L into delta cube into rho L minus rho V divided by mu L. Okay, so I have written all of these parts. So then I'll get an integral from 0 to 1 of, this will be eta minus eta squared by 2 from u, and then I'll have a HF minus CPL into Tsat minus Twall into 1 minus eta d eta. Okay, so if I now do this integration, one I'll have an HF and then the other I'll have this. So this, if I write a 3 here and a 3 here, so that it becomes easier to handle, then it becomes m dot prime of x on the left hand side multiplied by, there are two integrations that are there. The first integration will be HF multiplied by, this is 3 into 1 by 3, so that will get cancelled out, because we showed that eta minus eta squared by 2 here integrates to 1 by 3, right? So that term goes off. That becomes HF minus CPL into Tsat minus Twall multiplied by 1 by 8 into 3. So 3 by 8. This is the expression that I'll have. So if I look at this, I can cancel out. I can remove this because it has got cancelled out here. So the expression on the bracket is m dot prime x multiplied by HF minus 3 by 8 times CPL into Tsat minus Twall. Okay, so if I call this term as an effective HF as HF prime, okay, so this is a value representative of the whole film. The enthalpy is not equal to HF. It is not equal to CPL into Tsat minus Twall, but it is some fraction of Tsat minus Twall subtracted from HF. So I call this as HF prime. So I have this H dot at any x will be equal to m dot prime, which is the total mass flow rate, multiplied by an effective HF prime. Okay, so this is the expression that I would write. So H dot prime of x is equal to m dot prime of x multiplied by HF prime. Okay. Okay. So now, if I want to get the value of delta from the overall energy balance and mass balance, we'll be able to say that if I have a straight line profile of temperature from Twall, so if I say this is temperature axis and this is the y-axis, okay, and this is, if I say y by delta axis and y by delta equal to 1 here, at y by delta equal to 1, temperature is Tsat, and at the wall it is Twall. Twall is actually lower than Tsat, right? So I should draw it the other way around. Let me just do that. So this is y by delta, which is 1 here, so it is Tsat here, and here it is Twall. Okay, so this is a straight line that you would typically go with. Okay, so for this then the Q dot prime, that is the heat flux at any distance x, is going to be equal to the conductivity K liquid multiplied by Tsat minus Twall divided by delta. Okay, because the gradient at the wall is equal to Tsat minus Twall by delta. So this is the heat flux. So then if I look at the plate at any distance dx, if the heat flux is Qx, okay, so Qx into dx should be equal to the amount of condensation that happens between these two. So if I have an m dot at this location and m dot at this location, the difference between these two dm's, these two mass flow rates multiplied by hfg should be equal to the heat flux that goes into this. This is the expression that I'll be able to write. So if I write that as Q dot prime multiplied by dx is equal to dm dot into h prime hfg prime, right? So because m dot x into hf prime is at any x, so at x and x plus dx, if I write this, then the dm dot multiplied by hfg prime. So this is this is, I write it as hf. Okay, this is actually hf prime. Okay, let me okay. Okay, so the difference between these two would actually come from, there is a Hg that is coming from here. So if I look at this, there is a dm dot into Hg that is coming in from here, and there is a certain amount of energy going, and there is a certain amount of energy going here. So I have to write this expression. Just a second. Okay, so let us write the expression. This q dot into dx is the energy going out, is equal to the energy coming in from top is m dot prime at x into hf prime at x. hf prime is anyway the same value. Minus m dot prime at x plus delta x into hf prime. So those two come, and there is a thing that is coming which will be dm dot. So this is getting added, dm dot multiplied by hg. So if I can look at this, this actually becomes minus dm dot into hf prime and plus dm dot into hg. So it will actually become hfg prime, where this is equal to dm dot multiplied by hg minus hf prime, which is hf plus cpl into tsat minus twall into 3 by 8. Okay, so this becomes hfg. Okay, so hfg plus this. So I get is equal to dm dot into hfg prime, if you would like, where hfg prime is nothing but hfg plus 3 by 8 cpl into tsat minus twall. Okay, so if I write this as the expression, then I can get the expression for delta, because this q dot L is nothing but KL into Tsat minus Twall divided by delta to dx. Okay, so basically then this leads me to an expression which says, and I can substitute for m dot from here, m dot prime, this is actually. So m dot prime of x is given by this expression, okay, which is rho L into rho L minus rho V into delta cube G by 3 mu L. So dm dot so this dm dot can be written as equal to rho L multiplied by rho L minus rho V into G into delta square d delta divided by 3 mu L, and that multiplied by hfg prime is the expression that I would get. Okay, so now I have a differential equation for delta which I can solve, and that would give me the expression for delta of x. Okay, so I just integrate this expression. So all of this and all of this would be constant, and this delta can come here, so it will become delta cube d delta, and I integrate that. So delta cube d delta is equal to, I take all the other expressions to the other side. So I have there is a mu L by rho L, so I write it as mu L, and the expression and there's a 3, right? And there is a KL into Tsat minus Twall. Okay, so those are the numerators, divided by the denominators, which will be rho L minus rho V into G into HFG prime, okay, into dx. Now, I know that delta at x is equal to 0 is 0. So if I integrate this, I get a forced power expression for delta. So I get delta of x, you can verify this integration, is equal to x multiplied by 4 KL mu L into Tsat minus Twall divided by HFG prime into G into rho L minus rho V, whole thing raised to the power of 1 by 4. So it tells me delta is of the order of x raised to the power of 1 by 4. Okay. So once I have got this expression, I'll be able to write H at any x. This is not the enthalpy, but this is the heat transfer coefficient. Okay, this multiplied by Tsat minus Twall is actually QL prime. Okay, so we can write H of any x is going to be equal to Q dot prime at any x. This is x. Okay, divided by Tsat minus Twall. And since Q dot prime of any x is going to be equal to KL into Tsat minus Twall divided by delta, and this is Tsat minus Twall. So this gets cancelled, you get a KL by delta. Okay, so this is going to be actually equal to KL divided by delta, and delta expression we already have. So H at any x is going to be equal to KL divided by this. So that is the expression that you would get. So there is a KL already here to the power of 3 by 1 by 4, and there is a KL that goes, so to become KL to the power of 3 by 4. So that's the expression that you would get. This is going to be equal to KL cube into HFG prime to G into rho L minus rho V, okay, divided by 4 times x nu L into Tsat minus Twall, whole thing raised to the power of 1 by 4. So this is the expression that you would have. So this is the local heat transfer coefficient, and H bar at any x would be equal to integral from 0 to x times x times x bar would be equal to the integral of h of x dx. Right, so this will be actually, if I remove this x and bring it here, to be 1 by x. Okay, so if I do this, this will actually come out to be 4 by 3 times h at x, because there is a power 1 by 4, x to the power of 1 by 4. So if I integrate that, it comes. So I write nu bar at any L, that is at x is equal to L. That is, if I have a plate of length L, then the overall heat transfer coefficient for the whole plate of length L, the x will be replaced by L. This will be h bar at L into L by KL. Okay, so this actually comes out to, you can verify this, 0.943 times L cube into HFG prime into G into rho L minus rho V, okay, divided by KL into nu L into Tsat minus Twall, whole thing raised to the power of 1 by 4. Okay, so this expression is the Nusselt expression for film heat transfer. Okay, so basically if I have a falling film condensation, then in falling film condensation you get the Nusselt number given as this expression. Now this expression basically assumed that the temperature profile is a straight line, but if I could do a method, do the integration using proper integral method without assuming that straight line, you assume a temperature profile, substitute the boundary conditions and get the temperature profile, and do with that, then you get a better expression. So Rosenau relaxed linear assumption of T of y, and then he got HFG prime as HF plus CPL into Tsat minus Twall multiplied by 0.68. Okay, so if I call this one as the, if I divide it throughout by HFG, I get HFG prime by HFG is equal to, so this is HFG. This is equal to, okay, so if I divide throughout by HFG, I get, let me just do that separately here. Is equal to 1 plus CPL into Tsat minus Twall into 0.68 divided by HFG. If I call this number, which is CPL into Tsat minus Twall by HFG, as the Jacob number, this becomes 1 plus 0.68 into Jacob number. Okay, JA is called the Jacob number. Okay, so this in Nusselt expression, this was actually HFG prime was equal to 1 plus 3 by 8 Jacob number. Okay, whereas in Rosenau's expression, it becomes 1 plus 0.68 Jacob number, which is an improvement over the first one. Okay, so this is the expression that you get. So now substituting this, what we can say is that Q dot prime at L will actually be equal to H bar L into Tsat minus Twall. This you can easily verify. You can substitute, multiplied by the whole area of the plate, which is length multiplied by unit width, L into 1. This actually would be equal to HL by K is the Nusselt number, so it's Nusselt number into KL. So it is equal to KL into Tsat minus Twall into Nu bar L. Okay, and similarly m dot prime at L, which is the mass flow rate per unit width. This actually you can write from the energy balance as Q dot prime L divided by HFG prime. Okay, so this would actually become again KL. So Q dot L is actually this, and therefore this is KL by HFG prime into Tsat minus Twall into NUL. So these two expressions are valid for not just laminar, this is valid for all film condensation, including wavy and turbulent. Only thing is the corresponding NUL should be used and not the values that we used in the earlier part. But these expressions are otherwise valid in general. If I use these expressions that I already have for NUL, then it is only valid for laminar region. Okay, so that is using appropriate NUL bar. Now, if I use the NUL bar from this expression of Nusselt or the one that used from Jacob number, then I would basically get the QL and ML for laminar flow. Otherwise, I'll be able to get it for turbulent flow. Okay, so I'll stop this lecture here. We'll take this continued in the next class with discussion on what happens when I relax further approximations that I have made. That is, we have neglected the inertia terms, we have neglected the shear stress between the vapor and the liquid. So if I relax all of those assumptions, then what does the expression become? Let us look at that in the next class, along with further discussion on turbulent films and then about dropwise condensation. We'll stop for this class at this point. Thank you.